Hello, I'm Mahmoud Parham. This is joint work with Maciej Pacut and Stefan Schmid. In the balanced partitioning problem, we are given a set of n nodes initially partitioned into a number of clusters. A cluster represents a real physical server and nodes represent virtual machines hosted by these servers. Each server has a certain given capacity denoted by k. Therefore, there are n divided by k clusters, all with the same capacity k. The input to the problem is a sequence of communication requests. Each request is simply a pair of nodes which we depict as a graph edge. Requests arrive online, meaning an algorithm at any time does not know about the next or any future request. Moreover, algorithm must serve a request as soon as it arrives. Here we don't care what it means to serve a request. All we care is the cost of serving the request. In addition to serving a request, an algorithm can optionally move nodes between clusters at a cost that I will cover in a moment. There are two types of requests. Requests with endpoints within same cluster are served for free at cost 0. Requests between clusters, which we refer to as intercluster requests, are served at a cost always equal to 1. The second part of the total cost is the cost of moving nodes or migrations. Moving nodes can be arbitrarily expensive. The cost is same for all nodes and we denote it by alpha given as input. In this work, we address the special case of balanced partitioning problem, which we call the learning variant. In the learning variant of the perfect balanced partitioning problem, we assume the existence of a perfect partition. A perfect partition is a special partition that has zero cost for the input sequence. In other words, no edge ever arrives between any two clusters if nodes are partitioned according to the perfect partition. This implies that in this special case, we assume input sequences that allow such partition to exist. The perfect partition initially is not known to algorithms. The task of an algorithm is to learn or recover the perfect partition. In this model, the optimal offline algorithm moves to the perfect partition right at the beginning, which means the optimal offline pays only for node migrations, or optimal offline doesn't pay any cost for the sequence of requests. Let's see a running example. Assume the initial partition looks like clusters A and B on the left, where all black nodes are on cluster A and all red nodes in B. We assume the partition on the right is the target perfect partition, which is reachable by only swapping nodes Z and U. At this point, before any edge is revealed, an algorithm has no idea how the perfect partition looks like. Here is a sequence of requests that forces algorithm to make mistakes, but eventually it reveals the perfect partition to the algorithm. The first request comes between nodes U and V. After serving this request at a cost of 1, algorithm must collocate U and V. In fact, it must always collocate endpoints of every intercluster request, since by definition, a perfect partition never witnesses an intercluster request. A perfect partition never separates nodes that have an edge between them. So after serving this request, let's say the algorithm collocates U and V on cluster B, and in order to make room for the extra node, it moves some nodes, for example node X to A. As a matter of fact, it could be any other node instead of X. The next request is going to target whatever node algorithm chooses to evict at this point. The next request comes between nodes X and V. Let's say algorithm collocates them on cluster B, and again it has to evict some node from B in order to make a space for node X. Assume algorithm evicts node Y to cluster A without loss of generality. Similarly, the next request arrives between nodes Y and X, and the algorithm collocates the two nodes by moving node Y to cluster A. This time, node Z is the only isolated node left on cluster B, and the algorithm moves node Z to A to make a space for node Y. Clusters A and B on the right are already in the perfect partition, which means there can't be any more intercluster requests, and we are done. Notice that the algorithm made 3 wrong evictions until it made the right one, which was the node Z. We can generalize this sequence for any cluster capacity and any number of clusters. This is the idea behind our lower bound construction. I leave out all details of the lower bound proof and construction and instead give you a short summary. For the lower bound, we assume a perfect partition always exists. Any deterministic algorithm is doomed to make mistakes. Optimal offline knows the perfect partition and moves there right away at the beginning without paying for any request. By exploiting those mistakes, we get a lower bound linear in the number of nodes. Now the question is, can we get a matching upper bound? An upper bound linear in N. The key observation is that any competitive algorithm collocates the endpoints of each intercluster request, which means a complete partition after each such request. The partition that collocates edges revealed so far is not necessarily unique. If we choose this partition arbitrarily, then it leads to an n-square competitive algorithm. However, if we pick this partition to be the one closest to the initial partition, then we have an optimal algorithm, which is O of n competitive, matching our lower bound. To conclude this presentation, I briefly sketch closely related previous works. This problem has been extensively studied in the static offline setting. By static, I mean the assumption that optimal always moves to a certain partition and stays there permanently. The general online problem and the learning variant has been also studied with augmentation. By augmentation, we mean algorithms has the advantage of certain extra capacity on each cluster, while optimal offline does not have this extra capacity. Also, a lower bound existed before our work, but the lower bound was concerned with the special case of two servers and is linear in server's capacity. Our lower bound, on the other hand, works with any number of servers and is linear in the number of nodes.